Hello. In this video, we're going to take a look at the work required to pump a liquid out of a tank. So suppose we have some tank filled to some degree with water. And that fluid or water has density rho. Very often water, which we will state in problems, has density of 1,000 kilograms per meter cubed. When that's needed, it'll be stated. But in this case, we're just looking at a generic density of this fluid. And it's being pumped out of a tank that has a height of h. Could have an additional spout that is part of the height of the tank. This height is how far from the bottom of the tank to the spot that the water or liquid is being pumped out of. Find how much work is required, assuming the tank is full of water. We're going to look at this a little bit more in terms of just the tank has water. Might not be full because the tank doesn't need to be full for this integral to be set up. Now, as always, starting with our idea of work, work is force times distance. And since this is a vertical situation, we are looking at force being mass times gravity. And mass is density times volume. And this has that very similar setup to the pulling a chain up to the top of the building. But now, instead of the chain being just a straight linear object where we only need to worry about the length, now we have a 3D tank object where there's a little bit of volume to all of this. So let's look in at a specific little layer of water where we've divided this tank up into little tiny pieces of that yi minus 1 and yi that has a tiny little distance delta y. And we're looking at that layer of water, basically just skimming layer of water. And we know rho is constant and g is constant. So what we want to do is find this volume and find this distance traveled. The distance traveled, if we're looking at the water at layer yi, then the distance for the water to travel, if it has to get up to h to go out, distance is going to be h minus yi. How far does that layer of water need to travel? Volume, we're looking at a slice. We've done these slicing ideas before. When we took a look at volumes by slicing, what we wanted to do, like slicing up a loaf of bread, is there is a tiny little width or height to this layer of water, and then there's a surface area to this water. So using the idea of volume by slicing, some volume is going to be the area, the surface area of that layer of water, times the height, the width of that layer of water. So for one thin little layer of water to be pumped out, we have rho times g, which are constants. The height of the tank minus yi times the area at I times delta y. Same pattern as always. Add up all those little pieces of work to pump the water out. From I equals 1 to n. And take the limit as n goes to infinity. That is the work needed, which is also the integral of the water being pumped out, rho g, the height minus y, times some area function that's going to be in terms of y, delta dy now, because we've taken the limit. So here is our integral for finding work being pumped out of a tank. Biggest challenge is finding this area function. So taking a look at an example, we have a cone-shaped tank that has a diameter of 8 meters at the top, and it is 2 meters high. Not drawn to scale, but there is our tank. It has a diameter of 8. It has a radius of 4. It is 2 meters high. The depth of the water is only 1.5 meters, and the density of water is 1,000 kilograms per meter cubed. How much work is required to pump all the water out over the side? We have the integral from a to b of rho g h minus y, area of y, dy. And we can fill in a lot of this. A to B is where the water we're trying to pump out is. That is from the bottom of the tank at 0 to 1.5. Rho is our density of water, 1,000. G is gravity. We could put 9.8. I'm going to put G because I don't want to deal with 9.8. The height of the tank is 2 meters. And now the last thing we need is that area function. Like I said, the challenge of this problem. We want to figure out if at any point y, any height y, we can find the area of the surface of that water in the cone. Cone being pretty nice in that it has a circular top. So that circular top is telling us our surface area function is going to be somehow pi times r squared, because we've got a circle. At any spot y, I want to know, is there a way to find this r? Have here is really two triangles that are similar. They have two of the same angles. And they have two same angles, meaning they have three same angles. They're similar. So with similar triangles, we can set up a ratio of one side of the triangle over the other side is equal to the corresponding ratio. So using our big triangle is that it's 2 meters high with a radius of 4. There's our big triangle being formed by our cone. The smaller one is we're saying at any level y, I want to know the small radius. So putting those in the same spots, we have r over y. So 4/2 is equal to r over y. 2 equals r over y, or 2y equals our radius. So our area function is pi 4y squared. There's a lot of constants here. It's a very long integral, but ultimately this 1000g, just a constant, this pi, this 4, just a constant. So this is going to be 4000 pi g, the integral from 0 to 1.5 of 2y squared minus y cubed dy. We can evaluate that integral. If you work it all the way out, you'll get 4000 pi g times 63 over 64 joules. So it takes that much work to pump all the water out of this tank. Now, what if we only want to pump the top 1 meter? The inside of that integral is going to stay the complete same, because we still have this layer of water we're pumping out. The layer of water is still trying to make it up to the height of 2 meters to be pumped out. Everything is staying the same. The only thing that changes is the bounds. And the bounds changing means we're trying to pump out the top 1 meter of water. So the top is 1.5. If we're only down 1 meter from 1.5, we want to stop pumping water when there's 0.5 meters left in the tank. There's our new integral set up, doing the same constant pull out as before. We have 4000 pi g times the integral from 0.5 to 1.5 of 2y squared minus y cubed dy, which works out to be 4000 pi g times 11 twelfths joules. And if we actually want to find how much it takes to pump just that 0 to 0.5 out, it would be the difference between those two integrals. And so there is pumping water. In the next example, in the next video, we'll keep working with water, but we're going to leave the realm of work and go back to a force example.